This question talks about the combustion of methane, CH4, which produces carbon dioxide, the greenhouse gas, which can cause the Earth's temperature to rise. And it gives us, essentially, an amount of methane that we will burn, CH4, and a pressure and a temperature, and it asks us for the volume of carbon dioxide that is produced. So essentially what we're doing is we're combining two ideas, stoichiometry and the ideal gas law. So in all stoichiometry, we always need to start with a balanced chemical equation. So step one is to write this balanced chemical equation. So we have methane, CH4, in the gas phase, burning in the presence of oxygen, which comes from the atmosphere, to produce carbon dioxide and water. So one good thing about chemistry is this reminds you about combustion reactions. Stuff you learned before comes up again, and it helps us remember. So remember that when you're balancing a combustion reaction, you balance carbon, hydrogen, then oxygen. At least that's an easier way to do it. So all carbon of the hydrocarbon goes into carbon dioxide. So we have one carbon here, we're good. All hydrogen of the hydrocarbon goes into water. So we have 4 hydrogens here, and we have H2O here. So if we have 4 hydrogens here, we need 2 water molecules. That gives us a total of 2 oxygens here, 2 oxygens here, for a total of 4 oxygens on our product side, which means we need 2 O2s. We now have a balanced chemical equation. Next step is to figure out exactly how much carbon dioxide we could form. And to do that, we're going to need to use stoichiometry. So we're given kilograms of methane, which we can just simply multiply by 1,000 to get grams. So we're simply going, we're going from grams of methane to moles of methane to moles of CO2, because we're going to want to plug moles into PV equals nRT. So we don't want to go all the way to grams of carbon dioxide. So starting with 340 grams of methane times 1 mole of methane on the top, 16.05 grams of methane on the bottom, which was found just by adding up carbon and 4 hydrogens, times 1 mole of methane on the bottom from the balanced chemical equation, 1 mole of CO2 on the top. We find that this produces 21.1838 moles of carbon dioxide when we burn 340 grams of methane. We now want to figure out what the volume of this is. Well, if we have moles of a gas and we want to find its volume, we need to use the ideal gas law. PV equals nRT. In this case, we want to solve for V, so we start by dividing both sides by the pressure, and we get V equals nRT over P, which equals the moles that we just found, 21.1838 moles, times the ideal gas law constant, 0.08206. That's liter atmospheres per mole K for the units. I'm not going to write them all out. Times temperature, but the temperature has to be in Kelvin. This is at 12 degrees Celsius, so we need to convert that to Kelvin by adding 273 to it, and we get 285 Kelvin. Divided by the pressure is given as exactly 1 atmosphere. Simply multiply all the ones on the top and then divide by 1. You don't have to bother with that. B, in this case, equals 495 liters. To recap, we found the balanced chemical equation. We used stoichiometry to convert from grams of methane to moles of carbon dioxide. And then we plug those moles into the ideal gas law with the given temperature and the given pressure to find the volume of carbon dioxide that would be formed.